Thank you for the introduction. I'm Pooneh Nazari, and I'm going to talk about complex organic molecules in low-mass protostars. First, let's start with how protoplanetary systems, how planetary systems form. So it all starts from a big molecular cloud where the densities and temperatures are pretty low. Then the denser regions in the cloud start collapsing and they form the dark cores, and then they collapse even further and form protostars. At this stage, the densities and temperatures are much higher, and we've got envelope, we've got a disk, and we've got an outflow. And then once the envelope dissipates, we're left with a protoplanetary disk, which is what Alice talked about a few minutes ago. And then once the disk dissipates, we are left with a planetary system. For this talk, I will focus on the protostar phase and some of the most important questions in astrochemistry regarding this are, so are N-bearing and O-bearing species co-located in low-mass protostars? And is the formation pathway of a molecule universal? And are complex molecules formed primarily in gas or ice? For the third question, we really need to compare the results from ALMA, looking at the gas, with the results from JWST, looking at the ice. And you can see that this would be more of a thing that we can do once a JWST is launched. So for this talk, I will only focus on the first two questions. So you might ask, why do we really want to look at protostars or class 0 objects? The reason is that if we want to look at complex organic molecules, we really need to look at the most line-rich sources. Here I'm showing the spectra for two class 2 sources where they are pretty cold. And you can see in 40 gigahertz, we are seeing only 10 lines, and they are pretty simple molecules. However, if you look at the spectra for class 0 source, this is from the PIL survey, which is much younger and warmer. In 3 gigahertz, we are seeing 1,000 lines. So the line density is much higher. So to understand complex organic molecules, we need to look at these most line-rich sources. Also, planets, recently we have found that planets start forming in protostellar phase. This is a plot from Tyconic et al. 2020, where they find, where they look at the mass of solids in exoplanets versus stellar mass. And you can see that these these dots, they all fall on these shaded areas where they show the range of masses that we would see in class 0 and class 1 objects. Therefore, we really need to start making these planets at these early stages to have enough mass to actually make them. So if we want to understand the chemistry of planets, we need to start looking at the chemistry of these really early stages. So going back to the two questions that I mentioned, for you to understand the answers to this, at first I need to give you a general overview of how complex organic molecules form. So we've got a star, and it's got a big envelope, and the further you go, the icier it gets. So the temperatures are pretty low here, and we think that O-bearing and N-bearing species really form in the ice, and they get pretty complex already in the ice. Then when you get closer to the star, the temperatures increase, and we think that most of the oxygen-bearing species come off the ice at this stage. And then the closer you get, again, the temperatures rise even higher, and then we think that the N-bearing most of them come off the ice here. And in fact, Jorgensen et al. 2018 and Maniga et al. 2020 found, as part of the PIL survey, that there are two groups of molecules, some that they trace a larger area and have excitation temperatures around 100 Kelvin, and some that trace a smaller area and have excitation temperatures around 300 Kelvin. So I really want to emphasize that this has only become available to us because of ALMA, and ALMA has this really high resolution that we can really look at these sources on solar system scales. And also we can look at them in large frequency ranges, and therefore giving us more accurate excitation temperatures. And it's got a very high sensitivity that we can really look at the optically thin isotopologues of molecules, which can give a lot of information to us about the original molecule that is usually optically thick. So that's exactly what we did. We looked at two class 0 objects with ALMA band 6 with resolution of 0.45 arc seconds. And the cool thing about these two sources is that they are part of the JWST Guaranteed Time Observation program. And then we are guaranteed to observe these in ICES once JWST is launched. Here I'm showing the moment zero maps of SO and HNCO in these two sources and with overplotted with the continuum contours in black. And SO is known to trace the outflow. And here we can see beautifully that both B1C and S68N show these outflows as expected for very young objects. On the other hand, HNCO shows this compact emission, which is tracing the envelope and embedded disk. Which is more similar to what complex organic molecules show us. So another thing that I want to mention here is that our emission was unresolved and therefore the best we could do for assuming a source size was to assume a source size that is the same as the beam size. And this assumption is okay as long as the emission is optically thin and we are not looking at molecules with super high sublimation temperatures that they come off the ice really close in to the star. So what we did is that we looked at the spectra of these two sources and used cassis to fit N-bearing molecules, which is what I did, and O-bearing molecules, which is what Martin van Helder did. And just looking at this plot, you can see that the lines are very, very blended. And also our frequency range here, this is not the whole frequency range we had, but in general, our frequency range was not as wide as the PILS results. And these are really the two sources of errors in our excitation temperatures. So if I want to answer the first question that I mentioned at the beginning of the talk, are N-bearing and O-bearing species co-located? Then I need to really look at their excitation temperatures. And that's exactly what we did. So here I'm showing the excitation temperatures of the molecules we looked at in these two sources. And first of all, you can see that there is not much difference between the excitation temperatures of N-bearing species and O-bearing species. And also they all span a range between 100 Kelvin and 300 Kelvin. Another thing that we can do is to compare our excitation temperatures with sublimation temperatures. And that's why, because of this sketch that I showed you before, that we think molecules come off the ice at different temperatures. So the gray shows the sublimation temperatures from the lab results. And we can see some trends, for example, for a molecule like CH3 or CH3, where the error bars is pretty small, and it is showing a low excitation temperature and very low sublimation temperature. However, for most of the molecules, we don't see this trend, mostly because of the large error bars. But another interesting thing is that all the excitation temperatures are like larger than the sublimation temperatures. And this can mean that we are not really tracing the sublimation temperature with the excitation temperature, but a sort of average, so like a mass-weighted kinetic temperature. And perhaps the reason we are not seeing any difference between N-bearing and O-bearing species or these sort of trends in excitation temperature could be due to the fact that our error bars are just very big and we need better observations, basically, or larger frequency range. So going to the second question, is the formation pathway of a molecule universal? We can compare our results with other sources. So here I'm showing the column density ratio of our molecules with respect to methanol on the y-axis. And on the x-axis, for example, here, this is NH2CHO, and the different colors show the different sources that we are comparing ours with. So both high mass sources and low mass sources. And so showing you the rest of this plot, this is showing all the N-bearing species that we found. And so for some molecules like C2H5CN, we see that they are, this ratio is pretty constant between the different sources. And this is already very interesting because this could mean that this abundance ratio is already set in the cold phase prior to collapse and doesn't depend on the different sources. However, there are also some exceptions. For example, NH2CHO shows these variations between the different sources. I'll come back to this later, but first I want to show you what Martin van Helder did for the O-bearing species. So this is exactly the same plot that I showed you for N-bearing species, but now for O-bearing ones. And again, for most of the molecules, we see a constant abundance ratio between the different sources. But for some of them, again, we are seeing these large variations. Now the question is, so why do we see these large variations in abundance ratios? The first simple thing that we can think of is that basically the chemistry of these molecules becomes sensitive to the temperature of the region, the small scale structures that may be present, and therefore they could also have different formation pathways. For example, NH2CHO is known to have both formation pathways in ice and also in gas phase. And therefore, just depending on the temperature, you could suddenly start making them in gas as well. And this could make a difference. Another reason could be the different emitting areas of each molecule. I understand that this sentence is pretty vague, so I'm going to focus on this. I want to remind you that our emission was spatially unresolved, and therefore we can think of the scenario that I mentioned at the beginning, where some molecules are really emitting from a smaller area and some from a larger area. And we need to take into account for these different emitting areas in our calculation of column densities. So that's what we did. We looked at a spherically symmetric infalling envelope toy model with a power law in density and temperature. And what we found is that we need to multiply our column density ratios by a factor that ranges between 0.2, 0.1 and 2 for the sublimation temperatures that we have. So therefore, the differences that we are really seeing in abundance ratios between species and sources could be just partly due to the difference in emitting area and not really a strange chemistry difference that is going on. So to summarize, we found 4 N-bearing species and 10 O-bearing species towards these sources, and we didn't find any difference in excitation temperatures of N-bearing and O-bearing species, but this could be related to our large error bars, and the similarities of abundance ratios between sources could point us to the fact that some of these molecules, their abundance ratios are already set in the cold cloud, and the differences in abundance ratios could be either due to a different chemistry that is sensitive to temperature and substructures, or it could be due to a difference in emitting areas of the species. But I really want to emphasize that we need many more sources on the order of 100 with large frequency coverage to really be able to have some robust conclusions. Thank you very much for listening to me.